Hi class. Today we want to talk about two things, area under the graph and slope of the graph. Okay, so we're talking about our two basic motions, our constant velocity graphs, where our velocity is consistent and steady over time, unchanging, or velocity stays at the exact same level, or our steadily changing velocity, where our velocity is, let's say, increasing or decreasing. Okay. And we want to talk about a couple things. What does the area under a graph represent, and what does the slope of a graph represent? And we're going to talk about basically each graph. What does the area under a velocity time graph represent? And this would apply for both situations, both constant velocity and both steadily changing velocity. This is going to apply for both acceleration graphs, and this is going to apply for both displacement graphs. Um, So what we're talking about here applies to both situations. The area under the graph is going to be the same whether we're traveling at a constant velocity or whether we're changing at a steadily increasing velocity, and so on. Okay, so let's look at it. Let's begin with slope of the graph. So slope, if we look at slope, as you remember, is rise over run. Okay, so slope is rise over run. Rise over run. Okay, and let's look at this displacement graph because it's linear, so it's easier. And let's say we look at 2 points on this graph, here and let's say here. So our rise would be the y-axis. That would be a certain change in displacement. Let's say we went from 0 meters of displacement to, let's say, 12 meters of displacement. And our run, that's the change in x. Our run would be a certain amount of time. Let's say it took 4 seconds to do this, to do this change. So rise over run. In this case, our rise would be 12 meters and our run would be 4 seconds. And so let's just look at that. What do you think that means? If we change our displacement by 12 meters in 4 seconds, and we could simplify that to be 3 meters per second. What do you think that represents? Well, that represents the speed that we're traveling at. That represents the velocity. So by looking at the slope of the displacement versus time graph, we're able to determine the velocity. Oops, the velocity. Okay? So what does the slope of a displacement versus time graph represent? We're just talking about displacement versus time right now. The slope of a displacement versus time graph represents the velocity. Okay? All right, let's look at the slope of a velocity versus time graph. Well, we know under constant velocity the slope is 0, but let's look over here. Let's say we start out at let's pick a number. Let's say 4 meters per second of velocity, and let's say 1 second later we are at 7 meters per second. We've gone up to 7 meters per second, and 2 seconds later, now we're at 10 meters per second of velocity. So what would this slope represent? What would the rise? Okay, let's say here at 0 seconds. Okay, so we rose. Let's look at our rise. We went from 4 meters per second in 2 seconds to 10 meters per second. Okay, so in this case, our rise would be going from 4 meters a second to 10 meters a second. Our rise would be our velocity, our y-axis increased from 4 meters a second to 10 meters a second, increased by 6 meters a second. And our run, our x-axis, went from 0 seconds to 2 seconds, is 2 seconds. So what does that represent? 3 meters per second each second. That represents how rapidly our speed is changing, and that is called acceleration. Okay, that tells us the acceleration. Okay, 3 meters per second each second. 3 meters per second of speed change each second. That would be our acceleration. All right, and what would the slope of an acceleration versus time graph represent? It wouldn't represent, doesn't represent anything, okay? So, for our purposes anyway. So, the slope of a displacement versus time graph represents velocity. The slope of a velocity versus time graph tells us the acceleration. All right, and if you don't want to memorize that, just memorize the process and look at the units, right? Slope is rise over run. So on a displacement versus time graph, our rise is meters and our run is seconds. Meters over seconds. What is that? Velocity. What is rise over run on a velocity versus time graph? Rise is a certain change in meters per second, and our run is seconds. What is meters per second per second? Acceleration. Okay. All right, let's look at area under the graph. And let's start over here with acceleration versus time. So let's say our speed changes by 3 meters per second each second, and we do that for 4 seconds. Well, what happened if our speed changed by 3 meters per second each second for 4 seconds? What happened? Well, our speed went up by 3 meters per second in the first second, another 3 meters per second in the second second, another 3, and another 3. So altogether, it's telling us our speed went up by 12 meters per second. Okay, so, and area, think of area, just think of area as a rectangle. What's the area of a rectangle? Area would equal, let's say, base times height. Okay, so in this case, our base would be 4 seconds, and our height would be 3 meters per second, 3 meters per second of speed change each second, and if we multiply that, we'd get 12 meters per second. And this represents the amount that our speed changed during that 4-second time period. So this represents our change in speed or a change in velocity. Okay, so the area under velocity versus time graph tells us how much the velocity changed in that time period. All right, let's look at area under a velocity versus time graph. Well, let's choose this one because it's a little bit simpler. We can find the area under any shape, but let's just use this because rectangles are easy to work with. So let's say we're cruising along at a constant speed, 3 meters per second. Every second I cover 3 meters of distance, and I do that for let's say 4 seconds. Okay, 4 seconds. Okay, so what does this area represent? Okay, remember, area is side times side, base times height. So in this case, our base would be 0 seconds to 4 seconds. Our base would be 4 seconds, and our height, 0 meters per second to 3 meters per second. Our height would be 3 meters per second. And if we multiply those, we get 12 meters. Well, that would tell us how far we moved during that 4-second period of time. So the area under a velocity versus time graph tells us how far we moved in that period of time. So let's just say our change in distance or our change in displacement. Okay? And what does the area under this represent? Well, let's just look at the units, right? If we multiply this, if we took a little box in here, one side would be seconds, the other side would be meters, and if we multiply them, our units would be meters times seconds, which doesn't really mean anything in the context of motion, so we're going to call that nothing. Okay, so the conclusion is the area under an acceleration versus time graph will tell us how much the velocity changed in that time period. The area under a velocity versus time graph will tell us how much the displacement changed in that time period. And going kind of the other way, when we think about slope, the slope of a displacement versus time graph tells us the velocity, and the slope of a velocity versus time graph slope of a velocity versus time graph tells us the acceleration. Okay, so those are, you want to know both of those things, what the area under the graphs represent and what the slope of the graphs represents. All right, so let's look at some problems. Now, okay, yeah, we're going to do this problem two ways. All right, first way is the graph below represents the relationship between speed and time for an object moving along a straight line. So we have time on this axis, we have velocity or speed on this axis, and it's asking us how far did we go? Oops, sorry about that. What is the total distance traveled during the first 4 seconds? Okay, so then this graph actually shows us the first 5 seconds. So basically what it's saying is we can ignore this piece up here. We're only looking for the first 4 seconds. All right, now we said the area under a velocity versus time graph, right? Area side times side, meters per second times seconds will give us meters. And so we know that this area under here, represents the how far we went, the distance. Okay, and we know the area of, and these formulas actually are on the physics reference table. The area of a rectangle is base times height, and the area of a triangle is 1/2 base times height. Okay, you can think of this as a triangle cut in half. I mean, a rectangle cut in half. Okay, so we can use this formula. Let's get rid of this for now. Okay, so area is 1/2 base times height. All right, so what is our base? Well, our base is over here. The base of our triangle. It's 4 seconds. So 1/2 times our base, 4 seconds, times our height. Well, what's our height of our triangle? This is our height over here. So our height is, we went from 0 to 20 meters a second. So our height is 20 meters per second. All right, so now we multiply all that. We get 1/2 times 4 would be 2, and 2 times 20 would be 40. And if we look at our units, we've got meters over seconds times seconds. So this seconds is going to cancel with this second, and we're left with meters. Okay, so we just figured out the total distance is 40 meters by looking at the area under the graph. All right, now just to relate it to what we've been discussing already, another way, or the way that we've already been solving this problem, is by saying distance is equal to, or displacement is equal to, average velocity times time. Okay, and okay, well, we know time, right? It started here, and we're interested in the first 4 seconds, so time is 4 seconds. But what's our average velocity? Well, when we're steadily increasing, the average velocity is the midpoint of our starting velocity and our ending velocity. So we started at 0 meters per second, and we ended up here at 20 meters per second. Okay, so 0 meters per second to 20 meters a second. What's right in the middle of that? 10 meters per second. So our average velocity is 10 meters per second. And if we multiply that, we get 40 meters. Okay, so we can use to find, when we're given a graph like that, a velocity versus time graph, and we're asked to find distance, we can either use the average velocity times time method, or we could do area under the triangle, 1/2 base times height. Okay, let's look at another problem. Okay, so again, here we have another velocity versus time graph. We have speed and time. Okay, so base your answers to 16 and 17 on the graph below, which shows the relationship between speed and time for a car moving in a straight line. Okay, determine the magnitude of the acceleration. Well, acceleration, we said, the acceleration, let's go up a little bit. Acceleration, we said, is the slope of a velocity versus time graph. Acceleration can be found by looking at the slope of a velocity versus time graph. So let's just say here, start off at 0 seconds and 0 meters per second, and let's find a nice convenient point. This looks like a good point because we can easily tell what that is. It's right on a grid line. So And again, there's a couple ways to do this, but let's do it as slope. So slope is rise. So from here to here, what was our rise? We went from 0 meters a second to 10 meters a second. So our slope, which is rise over run, would be plus 10 meters per second. That was our rise. That's what we did. Rise over run. What's our run? Our run is 0, 2, 4, 6, 8 seconds. Okay, we went from 0 seconds to 8 seconds. So our run is 8 seconds. And that would give us meters per second per second. Meters per second per second. Meters per second of speed change each second. And 10 divided by 8, that's 5 divided by 4. That's 1.25. And that is our acceleration. Our rate of change of speed change. And we're done. The other way to do it would be to just use that formula that sort of defines acceleration, right? Acceleration is our change in velocity over time. And what was our change in velocity? 0 meters per second to 10 meters a second. So our velocity changed by plus 10 meters a second. What was our time that it took us to do that? 8 seconds. Gives us, of course, the exact same relationship, and we end up with, of course, the same answer. 1.25 meters per second of speed change each second. Okay, so that's just a couple. Oh, now let's do the second part of the problem. Then we'll be done. Okay, this is part 1. This is question 16. All right, question 17 down here. Calculate the total distance the car traveled during the time interval 4 seconds to 8 seconds. Okay, so we're interested in knowing how far did the car move from 4 seconds, which is here, to 8 seconds, which is here. Okay, so we're interested in this interval of time. How far did the car travel during this interval of time? All right. Well, we know that area is side times side, right? The height would be meters per second. That's and the base would be seconds, right? Seconds times meters per second is going to give us meters or distance. And so one way to solve this would be to find the area under the graph. So let's do that. So I'm going to, in order to figure out the area, I'm going to break it into 2 pieces. I'm going to break it into a rectangle, which is here, and a triangle, which is here. Okay. So what's the area of the rectangle? Well, our base, 4 seconds to 8 seconds. And we're going to do the area method over here. Okay, and we're going to start with this rectangle. Okay, the base, 4 seconds to 8 seconds. That's 4 seconds, time change. And our height, well, this right here is 5 meters per second, right in the middle of those two. It's logical because we're at 10 meters per second at 8 seconds. We're at 0 meters per second at 0. So right smack in the middle of 0 seconds and 8 seconds is 4 seconds. So we should be right smack in the middle of 0 meters per second and 10 meters per second. So this is 5 meters per second. Okay, so base, 4 seconds. 4 seconds to 8 seconds. That's a 4-second time change. Height, 5 meters per second. 5 meters per second. And that gives us 20 meters. So this rectangle would represent 20 meters of distance. Okay, and then we have to add this to it as well. So again, this is a triangle now, so it's 1/2 base times height. Okay, so now we have to add in this 1/2 base times height. So our base, again, is 4 seconds to 8 seconds. That's 4 seconds. Okay, so 1/2 times 4 seconds. And our height, well, here we started at 5 seconds, and 5 meters per second, and we went to 10 meters per second. So our height, this height here, is 5 meters per second. So times 5 meters per second. And if we multiply that, 1/2 times 4 is 2. 2 times 5 is 10. So this would represent 10 meters. So this part would represent 10 meters, this triangle. And if we add the 2 areas together, say our total distance is 30 meters, right? 10 meters plus 20 meters. All right, that's one way to do it. That's the area method. The other method is distance equals average velocity times time. All right. So from 4 seconds to 8 seconds, what's our time? Our time is 4 seconds. Okay, what's our average velocity? Well, in this time period, we started at 5 meters per second. We were traveling at 5 meters per second at the beginning of this time period. We were traveling at 10 meters per second at the end of this time period. So what's the average? What's right smack in the middle of 5 meters per second and 10 meters per second? 7.5 meters per second. Okay, so our velocity is 7.5 meters per second. We'll scrunch together there. And if we multiply that, I'll write it again down here. 7.5 meters per second times 4 seconds. Okay, we multiply that. 7.5 times 4 gives us 30. Seconds cancel with seconds. We're left with meters, and we're done. So I'm just saying that in this case, the area under the graph worked. Well, both methods are going to work. The area under the graph is one way of doing it, and average velocity times time is the other way of doing it, and they both work perfectly fine. All right, so in conclusion, what you should know is that the area under a acceleration versus time graph tells us the velocity. The area under a velocity versus time graph tells us the change in displacement. And this is area under acceleration versus time tells us the change in velocity, how much the velocity changed during that time. The area under a velocity versus time graph tells us how much the displacement changed during that time. Slope, the slope of a distance or displacement versus time graph will give you the speed or velocity. The slope of a velocity versus time graph will give you the acceleration. All right, so this is what you should know. Okay, everything down here is what you should put in your notes and kind of commit to memory. You need to know what the area under the graphs represent, and you need to know what the slope of the graphs represent. All righty, thank you.